we're going to power through some examples. Really, that's what this section is all about, just examples over and over of using these kinds of things. And let's start with, this is example 3 in the book, and we are going to fabricate a box. And for my students, this may look like a familiar problem. We did a similar one, but without the calculus in Algebra 2. We're going to take a piece of steel, cardboard, whatever, and we're going to cut corners at. And the corners are going to be x by x. The sheet of metal started at is a 25 by 20. And the question is, how can I maximize the volume of this box? Well, here's what we know. We know that when we make this box, that the height is going to be x, that the width is going to be 20 minus 2x, and that the length is going to be 25 minus 2x, which means that the volume of this box is x times 20 minus 2x times 25 minus 2x. And we can also specify that the domain of x has to be between 0 and 10. We can't cut out less than 0. We can't cut out more than 10 because we run out of space in the box here. So if you think about our strategies, we drew a picture, we defined a variable, we read the problem carefully, blah, 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 and we're trying to maximize volume. This is everything we need to know. So I'm going to multiply out. I could theoretically take the derivative of that, but it's an awful lot easier in this case to multiply out and write this as a cubic. And there's my cubic. Just as an aside, if you have two things, sometimes it's easier to just use the product rule versus multiplying. When you have 3, it's a lot easier to multiply it out, at least for a straightforward polynomial. So the derivative, the rate of change of volume with respect to x, is 12x squared minus 180x plus 500. And I know that extrema can be found at the endpoints or the critical points. So let's start with the critical points. The derivative is equal to 0. I could get fancy and do all the math, or I could just plug this quadratic into my quadratic formula. I actually have a program on my graphing calculator, which is pretty easy to write. And what it tells me is that I will get x approximately 3.681 or x approximately 11.317. And my endpoints, of course, are at x equals 0 and x equals 10. So I need to analyze these. Well, one thing I might notice is that that right there is not in the domain of my function, so I can cross it off. So therefore, my choices are the volume at x equals 0, the volume at x equals 3.681, and the volume at x equals 10. What I know is that this is 0 and this is 0 because I've either cut nothing out of the corners, which means I have a flat sheet of steel, or I have cut everything out of the corners and I have a vertical piece of steel of double thickness. And that means that this must be a maximum, since it starts at 0, goes up, reaches an extrema at 820, goes back down again. I could do second derivative test, but honestly, in this case, I don't really need to. It's a straightforward, simple problem, starting at a minimum, ending at a minimum. Therefore, my critical point must be a maximum. Interpretation. This is a very important part of a calculus problem. I need to explain what exactly I just found. The maximum volume of 820.588 cubic inches will be found when I cut out 3.681 inch squares. All right, for my class, why don't you go ahead and pause, do exercise 7 out of the book.